Module 2, Lesson 6, Polynomial Regression. For this module, we will be discussing the curve fitting techniques under regression, which is polynomial regression, by starting off discussing quadratic regression, and then its criteria for best fit, and then how errors are quantified using quadratic regression, and then move on to polynomial regression, and then its coefficient of determination. Polynomial regression is a particular regression technique which is higher than your linear regression. This is done on particular data sets whereby it is unfit for a particular linear regression. When we compare then a linear regression against a quadratic regression on a given particular set of data that is basically scattered, note that letter A is a linear regression and letter B is a quadratic regression, under which the quadratic regression would tend to have a lesser amount of error on each particular data set as compared to when using a linear regression. Under a polynomial regression, it's basically another way to fit your data by using this technique. If you require a particular function that is higher than a linear regression. For example, let's say we require a quadratic regression. Therefore, the general form of your function then for your quadratic equation would simply be a0 plus a1x plus a2x squared plus e. Note that this is the same function that is applied for your linear regression, except that you've added a new term, which is a2x squared. Hence, if we then continue to evaluate higher order regressions other than a quadratic regression, let's say a cubic regression, we simply add another term to represent its coefficient, which is usually a3x cubed. The residuals or errors in your second order polynomial function or quadratic function is defined to be like so, which is basically similar to your linear regression, whereby from the actual data value of y, we subtract the modal value of y. Using the best fit sum of squares of residuals having the same criteria as your linear regression, your sum of squares of residuals will eventually be this formula. And in order to minimize the error incurred on this particular criteria, we then apply again the technique maxima minima in order to evaluate the coefficient values a0, a1, and a2 on your given criteria. So this is done by simply obtaining the partial derivative of your SR with respect to a0, the partial derivative of your criteria SR with respect to a1, and the partial derivative of your SR with respect to a2. Upon doing so, you end up with this given equation. And if we divide 0 by -2 to transpose -2 to the other side, 0 divided by -2 is still 0. And then we simply, again, much like the linear regression, distribute the summation as well as our constants on each term on our given particular function. Thus, ending up with a sequence equation now like this, and this. Note that you could clearly see on this particular system of linear equation, the linear regression function, which was indicated by this portion of your equation. So this portion of the equation is your linear regression function. So in order to evaluate then your quadratic regression from your linear regression equation, you simply add your coefficient for your variable a2, which is in this case for the first equation is simply the summation of xi squared. And on your second equation, you again add another coefficient for your variable a2, which is in this case, it's the summation of xi cubed. Notice that there's an eminent pattern on your quadratic equation, as seen from the linear regression. We simply place this coefficient as your coefficient for A0 now, this coefficient as the coefficient for your A1. Therefore, on the third equation, you will notice that this coefficient now is placed as the coefficient of your A0. This coefficient is placed as the coefficient for your A1, and the coefficient for your A2 for the third equation would be summation of xi cubed. Note that there's also an eminent pattern on the constant on the left side of your equation. You have the summation yi here, you have the summation xi yi, and here you have the summation xi squared yi. This particular pattern is very important since this pattern would be evident on any particular polynomial regression technique. Continuing then, after evaluating now the coefficients of A0, A1, and A2 using system of linear equations, so you may apply here any particular technique like elimination, substitution, or even determinants now, since this is a 3x3 matrix, to solve for A0, A1, and A2. After solving for A0, A1, and A2, you then generate your second order model function or quadratic model function to be like this. And from which, on this given particular function, note that the error is already incorporated within that given function based from our given particular process. Therefore, on a cubic regression now, the general form will then take in another variable for the next term, which is A3x cubed. Note that this is the same general form for your quadratic regression, except that you've added another term, which is A3x cubed now. And the residuals on your cubic regression is still defined to be the sum of the squares of residuals, which ends up to be this given formula. Thus, if we apply that and use that same criteria for best fit, you'd end up with a formula for your sum of squares of residuals to be like this, which is again simply equivalent to your actual value of y minus model value of y squared. And then to minimize the error, we then apply the partial derivative for your criteria this time with respect to A0, partial derivative of your criteria with respect to A1, partial derivative of your criteria with respect to A2, and partial derivative of your criteria with respect to A3, giving us this given system of linear equation. And again, much like what we did on the previous technique, we simply transpose -2 to the other side. Having 0 divided by -2 gives us 0. And then distributing our constants on each term as well as the summation on each term of our given function. Therefore, giving us a simultaneous linear equation equal to this, 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 and this. Note that you could easily see the formula for your linear regression on this given particular system of linear equation, which is actually depicted by this portion of your system of linear equation, and your quadratic regression, which is this portion of your system of linear equation. And notice again that the pattern is simply retained. Therefore, in order to get our system of linear equation for a cubic regression, your first equation, we then simply add another variable A3 whose coefficient now is summation of xi cubed. On your second equation, we simply add a variable A3 on your quadratic regression with a coefficient of summation of xi raised to 4. And on your third equation of your quadratic regression, we simply add a variable a3 with a coefficient summation of xi raised to 5. Note that same pattern is seen on this given particular system of linear equation for your cubic regression. That is, much like your quadratic regression, we simply take this coefficient as the coefficient for a0, this coefficient as the coefficient for your a1, and this coefficient for your a2. Much like here, we did this, we take this as the coefficient now for your a0 on the third equation, this as the coefficient for a1 on your third equation, this as the coefficient of a2 on your third equation. Thus, on your fourth equation, this will then be the coefficient for a0, this will then be the coefficient for a1, this will then be the coefficient for a2, and then we simply add a variable a3 with a respective coefficient of summation of xi raised to 6, as seen from the pattern. And then much like what we've seen under your quadratic regression, and note the pattern on the left side of the equation, you will see summation y, summation xy, summation x squared y, therefore you'd end up with a summation x cubed y. This particular pattern, as I had mentioned, is very noticeable when dealing with any order of regression. So, when applying them, the values are substituted on your model function, and after evaluating that, we evaluate the coefficient of your determination. The coefficient of your determination will have that same formula for your quadratic regression, will have that same formula for your cubic regression, and will have that same formula for any order of regression, which is the summation of your standard deviation of y minus the sum of the squares of your residual divided by the summation of the standard deviation of y. Your SR, or sum of squares of residual, will eventually carry on with this formula, while your standard deviation of y will carry on with this given formula. Let's evaluate this example. We are to fit the following set of data points using this time quadratic regression. So onto which we determine the coefficient for our quadratic equation, which is a0, a1, a2, using our given formula. Based from our system of linear equation, we need to find the individual summations that will be needed for our given coefficients for our 3x3 system of linear equation. So we simply tabulate then the result, evaluating the summation of your x to be 15, the summation of your y to be 152.6. And then we individually square each value of x and then sum it up, thus giving us a summation of 55. We raise the individual values of x to 3, so we end up with and then sum it up, we end up with the sum of 225. And finally, we raise x to the 4th power, individual values of x, and then sum it up, ending up with a summation value of 979. And then we multiply your x with yi and a value of your summation to be 585.6, and then multiply the values of x squared with your y, giving us a summation of 2488.8. Therefore, your linear equation will eventually take in this summations as their coefficient, giving you an equation looking like this. And if you evaluate for your unknown variables a0, a1, a2 using any system of linear equation, you would end up with the following values for a0 to be 2.4786, a1 to be 2.3593, and a2 to be 1.8607. and then substitute that onto your model function, which eventually gives you a model function equal to this given model function, which is 2.4786 plus 2.3593x plus 1.8607. This is how you evaluate for your model function for a quadratic regression. And based on the tabulated results, if we then establish this coefficient of determination, we simply evaluate for the model value on each given value of x based from our given model equation. Thus, if we solve then the individual errors, which is done by subtracting your actual value minus your model value and squaring each value, we then end up with a total summation of square root of residuals to be equal to 3.7466. And then solve for the standard deviation of y by obtaining the average value of y and then subtracting the average value of y from your given yi, and then squaring this difference, thus ending up with a total standard deviation of y to be equivalent to 2513.3933. Using now these values to solve for the coefficient of determination with an average value of y equal to 25.4333, we then end up with a coefficient of determination equal to now this solution, giving us a coefficient of determination equal to 0.9985, which eventually shows us that your particular quadratic fit best resembles your given set of data because of the correlation coefficient, which is very, very close to 1. This ends Module 2, Lesson 6.